Every single second, there are trillions of biochemical reactions happening throughout the body that are mediated by enzymes. Enzymes are types of proteins, and they're generally sensitive to even slight changes in the environment, in particular things like hydrogen ion concentration. For this reason, the blood pH, which corresponds to the hydrogen ion concentration, needs to stay in a very narrow range, between 7.37 and 7.42. If the blood pH rises or falls by more than a few tenths of a unit, it can lead to death. Now, acids and bases are generated by cells all the time, so the body has a few mechanisms to deal with these molecules and keep blood pH within a normal range. The first scientist who studied one of these mechanisms was Robert Pitts. Pitts injected 150 milliequivalents of hydrochloric acid, or HCl, into his dog. He calculated that his dog's body had a total of 11.4 liters of water. So separately, Pitts put 150 milliequivalents of hydrochloric acid in a volume of 11.4 liters of water. The dog's pH dropped from 7.44 to 7.14, which is really low, but it's not fatal. In the water, the pH dropped from 7 to 1.84, which would have been enough to kill the dog instantly. Based on this, Pitts concluded that the dog must have had a buffer in its body fluids, and the dog concluded that he could no longer trust Pitts to take care of him. In everyday language, a buffer is something that acts like a protective cushion or shield. And the same is true of physiologic buffers. They shield or prevent the pH from rising or falling too fast. The reason the body needs buffers is that acids, or molecules that readily give up their hydrogen ion, are being generated by the body all the time. These extra hydrogen ions would shift the pH into the acidic zone, so the body needs a way to handle them without a major shift in the overall pH. To accomplish this, buffers can essentially take on some of these extra hydrogen ions, and therefore keep the pH from dropping too much. Buffers are usually a weak acid with its conjugate base, or a weak base with its conjugate acid. The weak acid could be symbolized as HA, where A represents molecules like fluorine or acetate. And the fact that it's weak means that it has a weak effect on pH, because it doesn't fully dissociate in water. As an example, let's say that we had 10 HA molecules in 1 milliliter of water, which is a small fraction. Now let's say only one of those molecules dissociates or breaks down into hydrogen and its conjugate base. So you have 10 HA breaking down to 9 HA plus 1 hydrogen plus 1 A minus. And they like to maintain this balance. So if we remove some hydrogen ions, another HA will dissociate and release a hydrogen ion in A minus, which maintains that equilibrium. And if we do the opposite and add a hydrogen ion, the A minus will bind to a hydrogen ion to form HA. Since it maintains this equilibrium, we call it an equilibrium reaction. By definition, this equilibrium reaction can move forward or backward, depending on the concentrations of the molecules. And this is known as Le Chatelier's principle. So let's imagine you've got this tank of water, which at any one time has a small amount of hydrogen ions floating around as well as a small amount of hydroxide ions that are in equilibrium with the water. Imagine that we add a strong base like sodium hydroxide, or NaOH, to the water. Since it's a strong base, the sodium hydroxide would dissociate almost completely into sodium ions and hydroxide ions. And the hydroxide ions would bind to any available hydrogen ions. And this rapid loss of hydrogen increases the pH really fast. If there's a weak acid around, though, then as the hydrogen ions are consumed, the weak acid would dissociate and more hydrogen ions would enter the solution, which prevents the pH from rising so quickly. Now, weak bases can also act as buffers. In water, weak bases grab some hydrogen ions from the surrounding water, giving its conjugate acid, BH, and leaving hydroxide ions to jump off. And again, just like with the weak acid, this is in equilibrium according to their concentrations. Now again, taking the water tank example, but this time if there's a strong acid, like hydrochloric acid, then it'll first dissociate into hydrogen ions and chloride ions. And the hydrogens react with hydroxides to form water. This results in more hydrogen ions relative to hydroxide ions, which ends up decreasing the pH and makes it acidic really fast. When the buffer's around though, more B- will turn into BH and replace the hydroxide ions, preventing the pH from falling too quickly and staying relatively neutral. Now, thinking back to the weak acid buffer, there's a rate of the forward reaction, where HA dissociates into H plus and A minus, and a rate of the reverse reaction, where H plus and A minus join to form HA. Equilibrium is reached when these two rates are exactly equal, and the concentrations of the reactants are stable. For every buffer, there's an equilibrium constant K, which is the ratio of the concentration of H plus multiplied by the concentration of A minus, all divided by the concentration of HA. What you'll notice is essentially products over reactants. So if the value of K is high, that means that at equilibrium, more of the acid is dissociated, and that means that there are more products, or hydrogen ions, and that means that there'll be a lower pH. If we rearrange this equation, we can solve for the hydrogen concentration. We can then take the negative log of both sides, which is also equal to the negative log of K minus the log of HA over A minus. And since the negative log of the concentration is equal to the pH, this equation becomes pH equals pK plus the log of A minus over HA. And this is the Henderson-Hasselbach equation that we've all come to know and love. This equation allows us to calculate the pH of a buffered solution by knowing the pK of the buffer, the concentration of the base form of the buffer, and the concentration of the acid form of the buffer. Also, if A minus equals HA, then we get the log of 1, which equals 0. So that means that when A minus equals HA, the pH equals the pK of the buffer. From that point, if we add more hydrogen to the solution, then HA goes up and we have the log of a fraction, which is a negative number, so the pH goes down a bit, so it's lower than the pK. On the other hand, if we take away hydrogen from the solution, then the HA goes down and we have the log of a number greater than 1, which is a positive number, so the pH goes up a bit, and it's higher than the pK. Alright, as a quick recap, buffers are pairs of a weak acid and a conjugate base form, which releases hydrogen ions when the pH starts to rise. Or a weak base in a conjugate acid form, which binds hydrogen ions when the pH starts to drop. So both resist pH changes of body fluids. And the pH of the buffered solution can be calculated with the Henderson-Hasselbach equation.